Yeah, very good morning. Am I audible?
Yes, sir.
Yeah, thanks. Uh, the screen is visible.
Yes, sir.
Yeah, any question regarding last class? Okay. So the last class we have seen the respect means how to find out the canonical form for a given second order quasi-linear PD. Okay. And if PDA is of certain type like hyperbolic or parabolic or elliptic, that you will decide based on the coefficients of second order derivatives by finding the respective discriminant, the sign of the discriminant, whether it's greater than 0, less than 0, or equals to 0 for all values of x and y. Okay, on that domain. Then we have now we are going to learn a transformation technique, okay, which will help us to solve this PD in more simpler way than other. Okay, because this will become simple when you will learn the technique, okay, and when you will do practice it. Okay, right. So the concept is also in the same line like we have learned for Laplace transform. We have also learned Fourier series and Fourier integral in the last semester course. Okay, so here I'm just going to recall very few things which may be relevant to our that transform technique that's known as Fourier transform. Okay, right. So first we have come down to from Fourier series to Fourier integral. Means when you make that elastic string which has tied up on like let's say on x-axis from 0 to L, then you have make it flattened, and then you are stretching along the x-axis and let it be means like infinity. Okay, then because means there is no boundary neither on the left hand nor on the right hand. Okay, so then you may not expect similar nature. Okay, or you may not uh, come up with the periodicity of the functions and so on. So what you will do in that such cases? Okay, so we have learned that this Fourier series of a periodic function of a period 2L is represented by this. Of course, we have certain assumptions that f is continuous, then only you can, this function is continuous at every point, then only you can write this equal sign here. And if it is not continuous at that point, then you will have the average of the left hand limit and right hand limit. You can recall that convergence theorem. Okay, right. And okay, here this notation Wn and this Wn is given by this and pi x by L, and it is easy to recall all the things. And these are the Euler's coefficients A naught, An, and Bn. Okay, so we had asked question ourselves what will happen if we let L is tending to infinity. Of course, here these Euler's coefficients, okay, we are not touching at this time. Okay, of course. Okay, then here this is a discrete version which you can say a summation sigma n equals to what to infinity. So when you are letting L tends to infinity, you are getting down to the continuous case. Okay, and then it's replaced by integration from 0 to infinity or minus infinity to infinity, whatever. Okay, depends. Okay, right? So discrete case you have sigma, and its continuous version is integral. Okay, when you're letting. Okay, and then we have come around with, come up with the formula which is known as Fourier integral representation of f. Okay, so that is here we have this f of x is has the following integral representation. So instead of summation, now you have the integral 0 to infinity. Okay, that a naught term, constant term, that is going towards 0. Okay, that's not present here. Other than that, what is that is a of w, b of w, cos of wx, sine of wx. Okay, so we have all seen all these story in the last semester, so I'm not going to recall all the things. So these coefficients, these Fourier coefficients, are Euler's coefficients a of w and b of w are represented by this integral formulas. Okay, so here a of w is equals to, you have this formula and this is there. Now we have discussed Fourier sine integral, Fourier cosine integral representation. What we have done essentially here. So if you have f is a odd function, so if f is a odd function, and you know this f you have, this is a bounded. Okay, we are not we are having this integral. It's an improper integral if you recall. Okay, this is improper integral and it is not easy to again deal with. So again you have to for dealing with the improper integral of this infinite limit, what you have to do is you have to divide from minus infinity to some point c plus integration c to infinity. Okay, that integrand is there, and then this separately you have to evaluate these two integral, and the first integral, if I want limit, let's take a tends to minus infinity integration a to c, evaluate this value. If it is a finite value, then we will say that is converges. Okay, similarly you can replace this by here integration c to a, limit a tends to infinity. Okay, and if this integral will this limit will exist, means like after evaluating this upper limit minus lower limit everything, and if you apply the limit and if you're getting the finite value, so then you will say that's converges. Okay, so finite value, first finite value again will lead to the finite value. So for existence of this or convergence of this complete integral, you need to have the convergence of the both of the integral. If one of them diverges, this entirely diverges. Okay, so assume that those things are satisfied. Okay, then if f is a odd function, then this integrand become odd, because cos function is a even function, f is a odd, so product of odd into even function is odd. Okay, and I hope you are able to recall what do you mean by odd function. Means f of minus x is equals to minus f of x. That will say that's an odd function. Then you have that some definite integral property, if you are able to recall, minus a to a f of x dx. If f is defined, well defined, and f is an odd function, then this value is 0. If f is even, you have 2 time integration 0 to f of x dx. So these things can be taken into account here. Okay, in similar, provided certain conditions are satisfied. Okay, so f is piecewise continuous and has a right hand derivative, left hand derivative, so and so, and that's absolute converges. This is required for Fourier integral representation. Then further, if f is odd, this integral a of w is, this value will become to 0. Okay, so you will only have this b of w present in the Fourier integral. So this term will not be there in the whenever f is odd function. So that will give you a Fourier sine integral representation. If you have f is even, so this b of w becomes 0, and you have only this first term of this integral will present in this integral representation, that is known as a Fourier cosine integral representation. Okay, so if you have been asked to find the Fourier sine integral representation or cosine integral representation, means whether function is odd or not. You see, again you may ask that, sir, we have told that when f is odd, when f is even, then is Fourier sine integral becomes a Fourier sine integral and Fourier cosine integral respectively. Okay. But what happens if f is not odd and even, and suppose you have asked to find the Fourier sine integral, cosine integral representation. So that is a special case when you can actually see that actual Fourier integral representation becomes the either sine or cosine. F is odd or even. If f is neither even nor odd, then what to do is you are forced to have the Fourier integral, Fourier sine integral representation, Fourier cosine integral representation by substituting a of w0 or b of w0 respectively. Okay, so for finding the cosine integral representation of a given function f, these conditions should satisfy. Okay, and further this whether f is odd or even doesn't matter. If you are interested in finding the sine integral representation, means you want this term to be there present, means a of w you are forced to put 0. Similarly, when you are interested in finding the cosine integral representation, b of w is 0. You are forced to put that, and you can derive this a of w from here. Okay, so this is what the answer for that question. Okay, so yeah, if this is a similar result which we have seen for the Fourier series. At a point where fx is discontinuous, the value of the Fourier integral equals the average value of the left and right hand limit of f of x. Means this is equality only when continuity. Okay, so so if it is not continuous, then it is equals to f of x naught plus f of x naught minus divided by 2. Okay, average of the left hand limit and right hand limit. Okay, at the point of discontinuity. Okay, so that we have already seen in the case of Fourier series representation of f. So I'm just not going with that. Okay, right. Now, so this is what I was talking about for your cosine integral. If you are asked to find the Fourier cosine integral representation, you are forced to substitute p of w is 0, irrespective of the fact that f is even or odd. But if f is even, you are directly put, means you are having that force, then p of w is 0. Okay, and Fourier integral representation of f reduces to this. So this will come 2 by pi, 1 by pi becomes 2 by pi because of that property, integration minus infinity to infinity, and here it was, now it is 2 time integration 0 to infinity. So this is called the Fourier cosine integral. So for finding the Fourier sine integral representation, you have to substitute a of w is 0. And then you have f of x equals to integration 0 to infinity b of w sine of wx t of w, where the b of w is 2 by pi integration 0 to infinity f of v sine of w. Okay, right. Now, so this is Fourier sine integral. Okay, in case of odd function, it will come naturally. Okay, right. So we have seen the examples of them. Okay, so you can go back and check those videos. Okay, that video you can check. There we have seen one or two examples for finding the Fourier sine integral and cosine integral representation. Now let's come to our business now. Okay, that's what that transform technique. Okay, so by looking at this sine integral, for sine integral, for cosine integral, we can define the Fourier cosine transform and Fourier sine transform. Okay, then later on we will define the Fourier transform. Okay, so for if you are going to replace this Fourier cosine integral, it is there. Okay, so if you replace this a of w, if I replace this a of w by a of w is equals to square root of 2 by pi. This is f cap and c w. So what that mean? Okay, I'm just going to tell you. This cap means transform. Okay, right. Now c is for stands for cosine 1. W is the variable because of this. Okay, this constant is here because of certain reason that you will understand just after some time. Okay, so that you can find the inverse Fourier transform, square root of 2 by pi and square root of 2 by, this is going to be 2 by pi whole square, right? Square root of 2 by pi whole square. Okay, so if you replace this a of w by this, okay, then you will be able to get the Fourier cosine transform of f. Okay, similarly, if you replace here b of w by square root of 2 by pi f cap and suffix is s now to represent it as a sign related to the sign. So that will give you the Fourier sine transform. Okay. Now inverse will be given from here. So inverse Fourier sine transform of f will give you f of x. What is this? F of x equals to square root of 2 by pi integration 0 to infinity f cap s of w sine of wx dw. Okay. So this will give you the inverse Fourier sine transform. Okay. Similarly, here also I can write, okay, this is going to be, you're going to replace it by this. So it's going to be f of x is equals to square root of 2 by pi integration 0 to infinity f c cap of w cos of wx dw. So that will give you the Fourier cosine transform of inverse Fourier cosine transform is given by this formula. Fourier cosine transform will be given by this formula. Okay, so these are the two forms, okay, which you have learned, which you're now going to learn. Okay, so this is what here. Okay, so I just discussed this too. Now let's take an example. Okay, so find the Fourier cosine transform and Fourier sine transform of the following function. Okay, so Fourier cosine transform, what it will be is going to be, you have this is going to be square root of 2 by pi integration 0 to infinity f of v time cos of wv dv. Now this is equals to, not that, see, function should be defined for 0 to infinity for finding cosine transform or sine transform. Okay, if it is not, you have to redefine it. Okay, so this is equals to square root of 2 by pi. You can just simply, so from 0 to a, f value is k, and for a greater than a value is 0. So integration 0 to a k time cos of wv dv. Okay, now if you further do that integration and square root of 2 by pi k time, so integration of cos is sine, right? Sine of wv divided by w 0 to a. Now you know sine 0 is 0. Okay, and you have square root of 2 by pi k by w sine of aw. So this will be the Fourier cosine transform. Now for finding the Fourier sine transform, you have, this is Fourier sine transform is in a similar manner. Okay, is going to be square root of 2 by pi integration 0 to infinity f of v sine of wv dv. So this is equals to square root of 2 by pi integration 0 to a k times sine of wv dv. Now you further, you can evaluate this integral square root of 2 by pi k by w with minus sine, right, cos of wv 0 to a. Now I will incorporate this minus sign inside. You have cos aw minus cos 0. That cos 0 is 1. So 1 minus cos. So this is going to be square root of 2 by pi times k by w times 1 minus cos of AW. Now you can again further, you can go for 1 minus cos theta is 2 sine square theta by 2. You can also go with more simplification. Okay. So this is the way for finding the Fourier cosine transform and Fourier sine transform of this function, particular function. Okay. Right. Now let's take one more example. Okay. So find the Fourier cosine transform of the function this. So I'm just directly jumping to the formula. For a cosine transform of f is going to be square root of 2 by pi integration 0 to infinity f of v cos of wv dv. Now this is equals to square root of 2 by pi. So integration, so f of v is 1 whenever 0 to 1. Whenever 1 to 2 it is minus 1, and whenever 2 to infinity it is 0. So you have integration 0 to 1 cos of wv dv minus integration 1 to 2 cos of wv dv, and because minus 1. Okay. So for 2 to infinity it is 0. Okay. So there is no need to write that term. Now you can integrate cos function. That's going to be square root of 2 by pi 1 pi w, the sine of wv. So upper limit to lower limit 0 to 1 minus sine of wv 1 to 2, right? So this is going to be square root of 2 by pi 1 by w. So sine of w minus sine 0 is 0 minus sine of 2w minus sine w. Oh, this is equals to square root of 2 by pi. You have, this is going to be 2 sine w minus sine 2w divided by w. Now you can further solve it out. You can write it is as 2 sine a cos a, means like 2 sine w times cos w. 2 sine w will go out, and you can have 1 minus cos w inside, and then you can further rewrite it 2 sine square w by 2. Okay, so you can do further that simplification. Okay, right. So this is what the for this example. Okay, now these are the other notations for Fourier cosine transform and Fourier sine transform, and these are the notations for their inverses respectively. Okay, and further, because they are represented by integral, and you know the linear property of the integrals. Okay, so you know integral is linear with respect to addition and scalar multiplication. So it is easy to follow that cosine transform and sine transform both are of linear operations. Means both are linear operations. They means you can apply them individually. Okay, so this is very simple. Okay, if you want to write for your cosine transform of this AF plus BZ, it is very simple to follow. It's a one line. So for your cosine transform of AF plus BG is equals to what? Is going to be square root of 2 by pi integration 0 to infinity. You have, this is AF plus BG of V cos of WV dV. Now you follow the definition. What you will get, I'm just writing straightforward, square root of 2 by pi integration 0 to infinity f of v cos of wv dv plus, so this is a time, right? It's not right, required, plus b times square root of 2 by pi integration 0 to infinity g of v times cos of wv dv. Now this is further, what is that term? This is going to be cosine transform of f, and second one is for your cosine transform of g. Similar for sine one. Okay, so they follow the linear rule. Okay, similar for sine one. Okay, right. So now why we are learning them is to solve differential equations. Okay, yeah. So certainly we need to know what are the Fourier cosine transform of derivatives. Okay, when they will exist or whatever. Okay, right. So here it is the result. Okay, which is again can be derived by following the product rule of integral. Okay, provided certain conditions are need to be verified. First condition is f be continuous and absolutely integrable on the x-axis. What is meaning of absolutely integrable? Means you have minus infinity to infinity mod f of x dx is finite. That's what the meaning of absolute integral. Secondly, f dash be piecewise continuous on every finite interval, and let, this is very important, that limit x tends to infinity, f of x tends to 0. Okay, so this is very important, that limit x tends to infinity, f of x tends to 0. Now, if I'm going to let me derive first this first equality. Okay, so Fourier cosine transform of f dash. Okay, that's going to be what? Square root of 2 by pi integration 0 to infinity f dash of v cos of wv dv. Now, what? As I suggested, you may go for the product rule now. So, the first term and second term you have to choose. Okay. So, this is as this integration of this term. So, cos of wv time f of v. Okay. 0 to infinity. I'm just putting them. This is, I'm just using this as a symbol. Okay. Otherwise, you have to put limit. Okay. So, you can also go for limit. Limit, you can say x tends to infinity. Let me put in this way. X tends to infinity, and this is x here. So improper integral. So 0 to x. Okay. And limit x tends to infinity. Minus, okay, minus limit x tends to infinity integration 0 to x. Cos the derivative is what? W times sine wv with minus sign. So plus w sine wv, and integration of that was f of v dv. Now, when you put v equals to 0, f of 0 cos 0 is 1. That's fine. But when you substitute f v equals to x, because that will become constant if you put it equal to 0. That will be completely independent of x, so you can apply directly limit. Now, if you put the upper limit, that is going to be cos wx times f of x. So let me write it further now. You may see square root of 2 by pi limit x tends to infinity. You have f of x times cos of wx minus f at 0 plus w time for your sine transform. That's right, for your sine transform of f. Okay, right? This is what Fourier sine transform of f. Okay. Now, what will happen to this? As x tends to infinity, since cosine function is bounded between -1 to +1. Okay. So you can use the sandwich theorem. Okay. That says that f of x tan cos wx will tends to 0 as x tends to infinity. Why? Because it is given to you this condition. This is required. F of x is tends to 0 as x tends to infinity. Okay, right? So this is what, so I'm going to use that condition now. So this is going to be, so far it is square root of here pi by 2. I should multiply and divide by this. Okay, because root 2 by pi is outside here. Okay, now if you go further, so it's going to be w time Fourier sine transform of w minus square root of 2 by pi time f of. So Fourier cosine transform of f can be written in terms of Fourier sine transform. Okay. Now, similarly, so this second one, I'm leaving this to you, okay, as an exercise. It's very simple again in the similar way. Fourier sine transform of the derivative is going to be minus WFCF, means Fourier cosine transform. So now, by using this, okay, I'm going to use now, I'm going to tell you that the following. So Fourier cosine transform of f dash is w time Fourier sine transform of f minus square root of 2 by pi time f at 0. Okay. Now also Fourier sine transform of f dash is Fourier sine transform is going to be minus w time Fourier cosine transform of f. This term will not come because of sine 0 is 0. Okay. And you use the product rule and apply. Now, these together, what it will give you, if suppose everything is fine and you can apply this Fourier cosine transform and sine transform to the second derivative. Okay. So, I'm just going to have this Fourier cosine transform of f second derivative is going to be w time Fourier sine transform of derivative f dash minus square root of 2 by pi f dash at 0. If those conditions are satisfied, it means in the similar way as for f. Now, this is further w time Fourier sine transform f dash I can use here. So minus w of Fourier cosine transform. So minus w square Fourier cosine transform of f minus square root of 2 by pi f dash at 0. So Fourier cosine transform second derivative will come in terms of Fourier cosine transform of f. Similarly, for Fourier sine transform of f second derivative will come in terms of Fourier sine transform of f. Okay, and now you can use them for finding certain special Fourier means the transform of some special functions. Okay, for which you know the second derivatives. For example, you have the following. So I'm just interested in the finding the Fourier cosine transform of this following function where a is greater than 0. Now, what I know, second derivative of x is going to be a squared time of x. Right? Now, take the Fourier cosine transform on both sides. So Fourier cosine transform of f second derivative is equals to a square, is linear again, okay? Fourier cosine transform of f. Now, Fourier cosine transform of f double dash, just now we have deriven, okay? It's going to be minus w square Fourier cosine transform of f and minus square root of 2 by pi f dash at 0 is equals to a square time Fourier cosine transform of f. Now since you know f, so what is f dash at 0? From here, f dash of x is what? Minus a time e to the power minus ax. Now this implies f dash at 0 is equals to minus a. Okay, you can substitute now. So this will give you a square plus w square time for a cosine transform of f. I've taken this on this side is equals to f dash at 0 is minus a. So a times square root of 2 by pi. So this will imply Fourier cosine transform of f is equals to a divided by a square plus w square times square root of 2 by pi. Yeah. So now in the similar fashion, you can find for sine ax, sine bx, cos ax. Okay. Product of these two e to the power ax into sine ax also. Okay. And so on. Okay. So in this fashion, you can find this for a cosine transform and for your sine transform certain function by using these equalities. And that is rather simple than going with the integral, those integration 0 to infinity. Okay. Right. Any question? Yeah. Any question? Okay. So let's proceed now. So we have the following Fourier integral representation of f. So now we are going to define the Fourier transform of a give certain function f. Okay, so where this Fourier coefficients are a of w and b of w are given by this following formulas. Now you substitute them a of w and b of w here. Okay, so what will you observe is if you replace it, what it will be is f of x time f of x equals to 1 upon pi is common to a this here. So you substitute here. So integration 0 to infinity. You have a of w is integration minus infinity to infinity. F of v, I think we have solved this already somewhere. Cos of w tv time cos wx plus, okay, plus integration minus infinity to infinity f of v sine of wv dv times sine of wx, right? dw. Okay, right? Now, since this is independent of these, I can take them inside, and what you can rewrite is 1 upon pi integration 0 to infinity. I may write it at infinity minus infinity to infinity f of v time We have already, I think so, we have written that sine of, cos of WV, cos of WX plus sine of WV times sine of WX dV dW. Now we have used this cos A cos B plus sine A sine B, cos of A minus B. So that is going to be 1 upon pi integration 0 to infinity integration minus infinity to infinity f of V time cos of WV minus WX dV dW. Now further you can write it as, so I'm just writing again that the same thing, integration 0 to infinity integration minus infinity to infinity f of V time cos of W time V minus X dV dW. Now cos function is even with respect to W, and W limit is 0 to infinity. I'm again rewriting it as 1 upon 2 pi. I'm writing this limit as now integration minus infinity to plus infinity integration minus infinity to plus infinity f of V time cos of W time V minus X dV dW, because of the fact that its cosine function is an even function with respect to W. Okay, f of V and dV, they are only related with this integral with the dV. Okay, so we can make this alteration here. Now, since by following the similar concept that cos function is even, okay, so one can claim, or you can say observe, that 1 upon 2 pi integration minus infinity to plus infinity integration minus infinity to plus infinity f of V times sine of W times V minus X dV dW is 0. Why? Because this sine function is an odd function with respect to W, so it should turns out to be 0. Now, I hope you have learned some Euler's formula e to the power ix is equals to cos x plus I sine x. Okay, so this is what now come into the picture is this will give you, this will imply now f of x is equals to 1 upon 2 pi integration minus infinity to plus infinity integration minus infinity to plus infinity. I'm writing it at f of V time cos of W time V minus X plus I time sine of W time V minus X dV dW. I hope you are comfortable with this I. Okay, right now, okay, we are just using that to represent as a complex number. We are not doing anything more than that. Okay, so now you can add, because this is zero term. Okay, if you include here, if you look at, means like if you linearize this integral, this will not contribute anything. Okay, now this will give you 1 upon 2 pi integration minus infinity to infinity integration minus infinity to infinity f of V time e to the power I W V minus X dV dW. So this is known as complex Fourier integral representation. So this is known as complex Fourier integral representation of given function f. Now, what we can do with this to define the Fourier transform, okay, that will also be discussed now. Okay, so you can separate this v with v and x with here. Okay, so now this will imply f of x is equals to 1 upon 2 pi integration minus infinity to plus infinity, integration minus infinity to plus infinity f of v e to the power I w v dv time e to the power minus I w x dw. Yeah, that also fine, I think so, right? It doesn't matter whether you first with here minus sign and then plus sign, doesn't matter. Why? Because minus w here also I can replace it by minus sign, and here is plus sign, here also minus and plus. Okay, I just wish to match with the textbook notations, but it really doesn't matter. Okay, so because the situation will be similar. Okay, when you multiply it by minus sine of minus theta is minus sine theta. Okay, and cos of minus theta is cos theta. So it really doesn't matter whether you write v minus x or x minus v. Okay, to this contribution, x minus v here. Okay, so here I just wish to make it here minus, and here I must make it plus. Okay, now I see this is a f cap of w. I'm going to write as 1 upon square root of 2 pi integration minus infinity to plus infinity f of v time e to the power minus I w v dv. And then f of x is equals to 1 upon square root of 2 pi integration minus infinity to plus infinity f cap of w time e to the power I w x dx. Sorry, dw. So I hope now you got the point here. Now this is f cap of w is nothing but is the Fourier transform of f. It's known as Fourier transform of f. And the second one is the inverse Fourier transform of f. Okay. And again, the notation is something like this. Okay. Fourier transform of f is equals to this. Fourier transform inverse of f is equals to this. Now we can talk about the existence of the Fourier transform. Okay, right. So this is I have discussed just now. I'm not going. I have just discussed everything. Yeah. So this is what f of w. This is what f of x. Okay, it's called the Fourier. So notations are like this. Okay. Now here is the result for existence of the Fourier transform. So when you talk about the existence means like if you want to evaluate Fourier transform certain functions, so you need to verify certain conditions. Okay, what are those? Is the first condition is this following integral converses absolutely integrable. F is absolutely integrable. And second thing is f is piecewise continuous on every finite interval. Then you can define the Fourier transform of f by the following formula, and its Fourier inverse transform is given by that. Okay. Not that you have here integration with respect to v, there you have integration with respect to w when you are going with the inverse Fourier transform. Okay, right? And there not plus, there is, here is minus, there is plus. Okay, right. Now let's take one example. Okay, let's take this example. Find the Fourier transform of f following given. Okay, let's take this. So the definition of f cap of w is equals to 1 by square root of 2 pi integration minus infinity to infinity f of v e to the power minus I w v dv. So this is the definition of Fourier transform if it exists. So the first point you have to look at is whether all the condition of the existence of Fourier transform satisfied or not. Okay, so for that purpose, you have to first find out what is integration minus infinity to infinity mod f of x dx. So this is equals to, f of x is 0 whenever x is lies below minus 1 and x is lies above 1. So it's going to be minus 1 to 1 and 1 dx. That you can simply find out 2. So this is finite, so converges. Now second thing is f is continuous, piecewise continuous. So at the end points minus 1 and 1 only need to check at x equals to minus 1 and at x equals to 1. And that is very clear that it's have jump discontinuity, right? So from 0, it is just suddenly jump to the 1 when x is minus 1. Similarly, when x is 1, it jump to the 1 to 0. Okay. So left hand limit is and right hand limit are not equal. So certainly f is piecewise continuous. Okay. Or having the point of discontinuities at x equals to minus 1 and at x equals to plus 1. Okay, so this is certainly, so second condition is f is piecewise continuous on every finite interval. Okay, right. Now you are ready to evaluate this integral value. Okay, so this implies Fourier transform exists. And this implies f cap of w is equals to 1 upon square root of 2 pi integration minus infinity to plus infinity f of v e to the power minus I w v dv, that's equals to 1 upon square root of 2 pi integration minus 1 to 1. F of v is 1 whenever minus 1 to 1, otherwise 0 e to the power minus I w v dv. And now you know how to integrate e to the power ax. Integration is e to the power ax divided by a square root of 2 pi e to the power minus I w v divided by minus I w minus 1 to plus 1. I is constant. Now this is equals to 1 upon root 2 pi, upper limit minus lower limit carefully. So when you put v equals to 1, you have e to the power minus I w minus e to the power plus I w. E to the power minus I w minus e to the power plus I w divided by minus I w. This is, you can write square root of 2 pi w, and you have this is minus I here. So you can multiply and divide by I, and you can use that property that I square is minus 1, I cube is minus I. Okay, right? So this is going to be I time e to the power I minus IW minus e to the power IW. You can leave it as it is, or what you can do is you can also use that formula that e to the power ix minus e to the power minus ix divided by 2I is equals to sine x. Okay, because of that Euler formula, cos x plus I sine x, it is also cos x minus I sine x, and cos x will get cancelled. You have 2I sine x. So you can also use that fact. Okay, so if you use this Euler's formula, so finally this will give you the Fourier transform of this is equals to 1 upon square root of 2 pi w. So this is going to be minus here e power IW minus, I'm just writing it again. So e to the power IW minus e to the power minus IW divided by I, multiply and divide by 2. Okay, so this is going to be sine of W. So this is going to be square root of 2 by pi. Okay, sine W by W. Now, what it will give you, okay. Now, if you look at back also, means this is a Fourier transform of f. Okay. Now, if you look at back, that's going to be Fourier inverse of this f is what? So this is means this is going to be 1 upon square root of 2 pi integration minus infinity to infinity f cap of w cos of wx, sorry, not cos, cosine, not cosine, e to the power iwx ew. So substitute this here, so you will have the value of this is nothing but the f. Okay, right. Right, so I have discussed this thing, right? Yeah. So now you can also identify the Fourier transform of the following function now. So first of the thing is this function is continuous everywhere except at 0. Okay, because 0 minus limit is 0, 0 plus limit is 1. Second thing is absolute integrable, integration 0 to infinity, e to the power minus ax dx is finite. You can find out that. Okay, because a is greater than 0. Okay, limit x tends to infinity to the power minus ax tends to 0 whenever a is greater than 0. So this integral will converge. So Fourier transform does exist. Now what further is you want, so therefore f cap of w is equals to 1 upon square root of 2 pi integration minus infinity to plus infinity f of v e to the power minus iwv dv. Now apply the limit. So here means like from minus infinity to 0, it is 0. 0 to infinity is f e to the power minus ax. So this will implies f cap of w is equals to 1 upon square root of 2 pi integration 0 to infinity e to the power minus av time e to the power minus iwv dv. So this is equal to 1 upon square root of 2 pi integration 0 to infinity. It is going to e to the power minus a plus iw v dv. And I'm leaving this as an exercise to you. Simple. It's very simple. It's going to be 1 upon a plus iw. If you can relate with the Laplace transform, that's up to you. Okay. So this integral value is going to be 1 upon a plus iw. So this is a Fourier transform of e to the power minus ax. Whenever, okay, whenever f is defined like this, f is greater than 0, it is this value, and x is less than 0, it is 0. Okay. So I have discussed this, right? Now, what about this function? Let's take one example. So find the Fourier transform of this f of x equals to e to the power minus mod x. So, okay, this function is continuous everywhere except at x equals to 0, right? Or not? Okay, it's also continuous at 0. Whenever x tends to 0 plus or x tends to 0 minus, it is tending to the same limit. So it's continuous everywhere. Moreover, this is absolutely integrable. That also you can do. So because this is even function, you have integration minus infinity to infinity mod f of x dx is equals to 2 time integration 0 to infinity f of x dx. Mod f of x also you can put, because see, mod whether you put or not doesn't matter, because e to the power is always a non-negative number. So this mod is doesn't require, and you can verify that this integral converges, means like finite value. Now, what else you require? Continuity. So continuity is there. So Fourier transform will exist. Now, so therefore, now Fourier transform of this function, let's find out, is equals to 1 upon square root of 2 pi integration minus infinity to infinity e to the power minus mod x time e to the power minus iwv dv. So x is v here. Okay? Now, this is equals to 1 upon root 2 pi. You have to substitute in minus infinity to 0. So for minus infinity to 0, v is mod v is minus 3, so e to the power v e to the power minus iwv dv plus 1 upon root 2 pi integration 0 to infinity e to the power minus v e to the power minus iwv dv. Now further you can write this as 1 upon root 2 pi integration minus infinity to 0. What you have is e to the power 1 minus iw v dv plus integration 0 to infinity e to the power minus 1 plus iw v dv. This integral value and this integral value you can find out. So this is equals to 1 upon root 2 pi. So what will be the value of this integral? You have e to the power 1 minus iw. Okay. And this is a v. Yes, what we can say here is yeah. Okay, so tending to minus infinity, right? So if you put upper, if you apply this is going to be e to the power 1 minus iw v divided by 1 minus iw and plus e to the power minus 1 plus iw v divided by 1 plus iw. So here limits are 0 to infinity and here limits are minus infinity to 0. You have to apply in the limit way. Okay. I'm just leaving it to you, okay, that part. Okay, that rest of the part. Okay, so let me look, let me put it here. So limit a tends to minus infinity. Here a, this is b, limit b tends to infinity. So this is a and this is b. So limit a tends to minus infinity, and this is limit b tends to infinity. Now put upper limit minus lower limit, that is going to be 1 upon square root of 2 pi. Now 0 is equal to 0. So e power 0 is 1, 1 upon 1 minus iw minus, if you apply the limit, a tends to minus infinity, doesn't matter. So second term is e to the power minus a time 1 minus iw. Okay, so that a tends to infinity, a tends to minus infinity, this entire term will tend to 0. Okay, by Sandwich theorem. Now similarly here, plus, now when you apply here upper limit b tends to infinity, this tends to 0, minus lower limit. So you have 0 minus 1 upon 1 plus iw. So this is equals to 1 upon square root of 2 pi. Now 1 upon 1 minus iw minus 1 upon 1 plus iw. So if you take LCM now, okay, so what you will get is 1 plus iw minus 1 plus iw. So 2 iw divided by 1 minus iw into 1 plus iw, a minus b into a plus b, a square minus b square. So it's going to be 1 plus w square. Okay, so this is going to be the Fourier transform of the given function. Okay. Oh, we have missed one. Wait a minute. I have missed this minus sign here when you integrate it. So this is minus, this is plus. So this is going to be 2. So this is going to be square root of 2 by pi divided by 1 plus w square. Right. Yes. Okay. So do you have any question? You can ask. Okay. So now what we can do is now we can learn the Fourier transform of its derivatives now. Okay. That is our goal actually. Now, the very first thing is the property. One of the property is very straightforward. Fourier transform, we follow the linear rule. Okay. So provided both the Fourier transform of f and g should exist. Okay. And also the Fourier transform of af plus bg exists. Okay. Right. So then you can apply individual Fourier transform and then you can scalar multiply and you can add them. Okay. So linear property of the Fourier transform is there. Okay. Now Fourier transform of its derivative. So since you are going to apply here, if you look at back for in the Fourier transform definition, you have the limit from minus infinity to plus infinity. So this condition is very much required. Fx should tends to 0. Whether so as mod x tends to infinity, what does it mean is x tends to infinity or x tends to minus infinity. So limit x tends to infinity, f of x is equals to 0, and limit x tends to minus infinity, f of x is 0. Both should be there. Okay. Further, f is continuous. Of course, it is obvious. Why? Because f dash, whenever differentiable, it should be continuous. Okay. So continuity must be there, and it should tend to 0 as whether x tends to infinity or x tends to minus infinity. Then Fourier transform of its derivative is equals to iw time Fourier transform of f. So this again will go in the similar way, okay, as like in Fourier cosine transform and Fourier sine transform. we have seen. Okay. Now, what is the beauty of this Fourier transform here is you don't need the initial condition. So in the Fourier cosine transform, if you go back and check Fourier cosine transform of its derivative was something like Fourier W time Fourier sine transform of f minus square root of 2 by pi time f at 0. So f at 0 is required whenever you are going to attack to the a differential equation to solve. You require additionally initial condition. Likewise, also in Laplace transform, also you have seen in order while you solving ordinary differential equation by the help of Laplace transform, you need to have the initial conditions. But Fourier transform doesn't require that. Okay, right? Okay. So now we will take the help of this, okay, to solve PD. Okay, you can also solve the OD. You can take that also. Okay, right. So like in the Laplace transform case, there was a convolution theorem. Okay, what it was telling is that Laplace transform of the convolution of two functions was the product of their Laplace transform, f of s into g of s. And there the Laplace there the convolution definition was different than this. Okay, if I recall, what was the convolution there was f star of g in the case of Laplace transform I'm talking was integration 0 to t f of u g of t minus u du, if you recall. If you're able to recall, that was the convolution in case of Laplace transform. But here it is different. So don't confuse or don't take all the both the definition as same. So convolution here is different. There was different. Okay, right? So now, so here the convolution definition of the convolution of two function is given by this f of u times g of x minus. So this is okay. But here limits are minus infinity to plus infinity. And you can also verify that instead of means f, you can use z, and g, you can also exchange the role of f and g. That's what it means. Okay, means it depends. That definition of the functions you can say means accordingly you can decide which one you will take f and which one you will take g. Okay, right. So the convolution theorem for this states the following is that the Fourier transform of the convolution is the product of proportional to product of the Fourier transform of their individual. Okay, so proportional constant is square root of 2 pi. Okay, so this will help you in finding the inverse Fourier transform of product of two Fourier transforms. Okay, likewise we have taken advantage the convolution theorem in the case of Laplace transform. We can also take the advantage here. Okay, so if you have the Fourier transform of if you can you have suppose just now you have learnt, right, 1 upon 1 plus w square times square root of 2 by pi was the Fourier transform of e to the power minus mod x. Just now we have seen. Okay. Now also we have seen the following the square root of 2 by pi. I think that a divided by a square plus w square was the Fourier transform of e to the power minus ax, that definition. So if you make the product, you can use this convolution result here to find the inverse Fourier transform of these two products. Okay, provided you should be able to recognize, okay, this inverse Fourier transform of these two. Okay, so again this will come through the practice. Okay? Without that it is not possible. Okay, right. So now let's take one example of a PD and try to solve it by using the Fourier transform. So let's take the heat equation. Okay, let us take the heat equation. What is that? Ut equals to c square uxx with initial condition is ux comma 0 is f of x. Of course, we are having x is from minus infinity less than x less than infinity because we are going to apply the Fourier transform. And t is greater than 0. Is a time parameter right now. So we are going to apply the Fourier transform. So certainly we are going to apply the Fourier transform with respect to the space variable, that is x, because that is only varying from minus infinity to plus infinity. So Fourier transform of u of x comma t we can define as u cap of w comma. I'm taking Fourier transform with respect to x. Now, like we have discussed earlier, okay, Laplace transform case, you can show that Fourier transform of ut x comma t is dou u cap by dou w comma. You can simply interchange the role of derivative and integral. Further, you can also have this uxx with respect to x comma t. You have seen, okay, I'm just going to recall the following. Fourier transform of f dash, if you recall, that was iw time Fourier transform of f. So here 2 time derivatives, so it will be 2 time here I of w. So it is going to be, you can verify that I of w square time u cap of w. Okay, so from here you can verify, I'm just giving you this Fourier transform of f nth derivative at x. You can verify that's going to be iw to the power n Fourier transform of f. Keep on applying this, you will get that. Provided those conditions should be satisfied, right? F second derivative, F third derivative, and so on, F up to n minus 1th derivative. That should tends to 0 as x tends to infinity or x tends to minus infinity. That is required. Okay, so this you can verify. So now you have all the information now. You can use this, you can apply the Fourier transform in 1. Okay, so from 1 we get, what we get is dou u cap by dou t is equals to iw whole square time u cap of w comma t. C square was there, right? C square. Now I square is minus 1, so it's going to be minus c square w square u cap of w comma. Now this you can treat as a first order differential equation, linear first order differential equation with respect to time. Okay, and you can certainly show that what will be the solution of this u cap of w comma t is equals to some a of w time e to the power minus c square w square t. You can verify that. With respect to time, it could be a function, okay, constant could be a function of w. Okay, a of w time e to the power minus c square w square t. You can find the integrating factor and you can see. You can verify that. Now this initial condition u at x comma 0 equals to f of x will implies u cap at w comma 0 is equals to f cap of this Fourier transform of f. If you take the Fourier transform on both sides, t equals to 0, so you will get this. So now utilize this here. What will give you is this implies u cap of w comma t is equals to, if you put t equals to 0, this coefficient is e to the power 0 is 1, you know. A of w is f cap of w. So finally, this implies this is going to be f cap of w time e to the power minus c square w square t. Now you can take the Fourier inverse Fourier transform with respect to space variable. So this will imply, okay, u of x comma t is equals to 1 upon square root of 2 pi integration minus infinity to infinity u cap of w comma t time is going to be e to the power minus I w x dw, right? Inverse side plus. Okay. Now u cap of w comma t you can substitute here now. So this will be giving you the formula. Fine. Square root of 2 pi integration minus infinity to plus infinity. Now f cap of w now you know, right? What is f cap of w? Is I will write it. Okay, e to the power now minus c square w square t e to the power I w x dw. Now what will be further? This implies u of x comma t is equals to 1 upon square root of 2 pi. So 1 upon square root of 2 pi, one more time it will come from here. So it is going to be 1 upon 2 pi time integration minus infinity to plus infinity, integration minus infinity to plus infinity, f of v e to the power minus I w v dv. That's going to be f cap. And you have, this is e to the power minus c square w square t. And you have e to the power iwx is there, right? So you can club it together, plus iwx dw. Okay. Now based on the definition of f, now you can have that temperature distribution. Okay, right. Similarly, you can go for the wave equation. Okay, you can also go for wave equation. You can also solve that. Okay, if you have any question, you can ask. Okay, so like, okay, we have fine. So we have completed the content of the course. Okay, so far, and we will see okay, some of the application in the upcoming lectures. We will try to uh, look at them. Okay, meanwhile you try to uh, uh, make it ready, this project report. Okay? And I have also given you the deadline, right? 2nd of December. Okay, fine, thank you. If you have any question, you can ask. Or you can,
Excuse me, sir.
yeah.
Actually, the deadline for project report submission is 1st December and that video submission is 2nd December. So,
Both will be
will-
both. I will update it.
okay. And is there any possibility of extending the deadline?
Extending the deadline, then it will be extending your Viva time as well. Okay. So,
Because many students have requested me to ask you if it is possible to extend the deadline.